Alright, time for another DraftPhysics.com, debatephysics.com, also video presentation. So I found another kind of obscure channel. Physicist, seems like a smart enough guy, seems like he's probably not going to be a snowflake or a teardrop or whatever. That he can take a little criticism, maybe engage in conversation. He seems to wish to solicit people's questions and that kind of thing. I don't know exactly what this channel's about. It seems like they're doing some sort of courseware for some sort of purpose. Yeah, so way underviewed, I'd say, but whatever. So it's sort of a chat kind of thing, live room kind of stuff, so it's not as organized as a regular physics lecture. But he does have, he is talking the subject. So he's on the subject of thermodynamics. So I thought I'd just play some of this and see if I can provoke him to talk about the real implications. Thermodynamics is just energy moving through the universe. And it's still the same subject as what is the nature of this stuff, energy. Because heat is momentum. It is heat. It's movement. It's matter moving. It's something else. And it really shows the fact that it never dies. It never stops being energy. And it's always going somewhere. And this is really, it's such a foundational bit of understanding to understand that the movement always is somewhere. And when it's inside of something, it's just this stuff moving. It's just little bits moving. And it happens to be trapped inside of a material system in terms of pushing electrons and protons, but it's always doing that, and then you can just return it to basically being free again. So energy is either in the form of being free, flying through space at the speed of light, or it's pushing a piece of matter, an electron or proton. And that is, I'm just arguing, I think the facts all point to that being the reality, and there's nothing else involved. There's just two states of energy, free and obligated to push something heavier than it is. And that's it. It's a push-averse. And that's all it is. Yeah. So anyway, let's get to it and such. So, guy's name is Billy. Seems, like I said, kind of receptive to conversation, perhaps. We'll see. I guess I'll just say right in the beginning, just in case he's only going to watch 10 seconds. Let's just do the train thing, okay? 5-ton train going 10 miles an hour, 10-ton train going 5 miles an hour, tug of war. Now, kinetic energy says the 5-ton train going 10 has twice as much energy. Do you think that'll be proven by the experiment? The rope runs out, they both stop, that's it. The 5-ton train is not going to drag the 10-ton train with it. You kind of know it, right? And it's a decisive piece of evidence, right? It just basically says there's no way it has any extra energy. It doesn't have any mv squared. It just has mv. MV moves spaceships. MV is thrust. MV is the only thing that actually, works on a lever. Weight. It's MV. Come on. Do you have any counter argument? Any counter evidence? No. It's got to be. This fable. It's got to be ended somewhere. And since you're on the subject of thermodynamics, we'll get to the fable of the second law. He's actually talking about the first law here, so we'll see if we get to the second law.
Principle can happen without violating the first law of thermodynamics, i.e. conservation of energy, but it never happens.
So he's just talking about the fact that there's lots of things you could say that would be breaking conservation of energy, but they don't happen. But I'm saying there wouldn't be a breaking of conservation of energy. So, you're just talking about systems changing. You have to consider the complete change in the sense that the energy has a complete history and it has a complete future. And so you have to alter the complete future to alter what you're going to argue could possibly happen in the present. So you have to make something happen to the energy to make it reverse. So none of this stuff is reversible.
So, for instance, one thing that could happen is I could take let's say, a hot piece of iron and stick it up against the ice cube. Okay. And I could just let that ice cube and hunk of iron sit next to each other. And what's going to happen is
I'll just go a little bit ahead because I heard this part before and it's a little bit longer than it needs to be. Yeah, it's going to melt the ice, the heat, the action, the activity. There's more activity in one object than there is activity in the other object. And obviously the activity level is going to go like sound or anything else that's going to pollute in one direction. Sound, quiet doesn't move into noisy places, and noise moves into quiet places. So there's lots of analogies to describe the fact that whatever contains the most density is going to pollute the thing with less density.
heat's going to flow from that hunk of iron into the ice cube, and the ice cube is going to raise its temperature. Maybe the ice cube was at like negative 20 degrees Celsius initially and was, of course, frozen. So what's going to happen is heat's going to flow out of that ice cube, or excuse me, out of that hot iron.
So I could probably even still go further. Yeah, so he's talking about the real case, and he's going to say it is possible for it to go the other way. But it's only possible in some sort of infinite number of permutations to make it possible, in the sense of something has to take all of that energy that's going the wrong way. I mean, every kind of direction. So it all has a future. And somewhere in the future, every piece of it has to be reversed. That is, some obstacle has to be in the way to cause the energy to go in reverse direction. And there's nothing, there's no shape, that is going to be able to create that reversal. There's nothing I could build. Like I could, if all the energy was going one way, well, it'd be easy. You just put a block in front of it, you just reflect all the energy. But the energy is going in all directions and at different path lengths. So I can't make a circle. I can't make any common shape. I have to make some bizarrely unusual shape, like Bugs Bunny, for the reflections to happen at all the right locations to cause the reversal. And you're talking about a million, different little pieces of energy that have to be reversed at exactly the right time. And the probability of that happening is zero. There's just no chance.
/ water mixture. And in so doing, that would actually cool down the ice from 0 degrees Celsius, and the mixture of water and whatever temperature it is, it would actually cool that ice and that water down and freeze it while warming up the.
So he's basically saying you could have this condition where the ice just happens to pump more heat into the hot thing than the hot thing pumps into the cold thing. But again, it will require a circumstance of zero probability. I mean, it'd just be the unlikelihood of it happening is so extremely high because it has to coincidentally hit all of these stupid pieces of energy at just the right time to reverse their direction. So it's not going to happen. Let's see, can I just hit my space bar?
The actual chunk of iron. None of that would violate the first law of thermodynamics, but we know it doesn't happen. Okay? Another one, which you've probably seen videos of before, is something like a coffee mug or a hot tea glass sitting on a table. You could, in principle, imagine it getting knocked over. It would then fall down and hit the ground and shatter, and the tea would splash all over the place. In principle, without violating the first law of thermodynamics, which is, again, conservation of energy, you can see the water molecules, or the tea molecules, I should say, jumping out off the floor, coming.
Right, but you know that all of that energy, so that energy flow had a future. So when you broke it, there was a future for all of those little bits of energy. And the only way you can reverse it is that every one of those little bits of energy has to be reversed perfectly. Or you could say before the cup hits the ground that somehow you've created a condition that's perfectly reflexive, in the sense that somehow Well, it has to break it first, right? So it has to always break it. So you're stuck with that future problem. So you're going to take energy that's going in one direction, you're going to scatter it into 7 million different directions, all coming from different ways. So you almost have to have gamma ray come down to hit the little piece of the teacup or the liquid. And you have to have another gamma ray come over this way and hit it just right or something, because there's no way to compensate for the fact that it is energy and it is moving in a direction. And there has to be some force that counters that to reverse it. It can't just stop it from moving, it has to reverse its motion, which is even more difficult. So it has to have enough energy not to just stop it from moving, but it has to reverse its motion and force it to go the opposite trajectory. So just no possibility, frankly. I don't think it's even possible, let alone just being improbable. But whatever. Won't argue the difference between impossible and infinitely improbable.
Together up in the air in roughly where the shards of glass are going to reassemble themselves into the shape of a tea or coffee cup. And then that.
So in a sense, you have to have energy that has exactly the opposite energy profile coming from the opposite direction. Again, it's not just enough energy to stop the tea from moving. You have to reverse its direction. So it's like you have to have twice as much energy doing exactly the opposite of what the teacup pieces are doing. And again, even having them have the stopping energy is improbable. Having twice the energy makes it impossible.
Tea or coffee cup could take that energy that it has that's due to it slightly being warmer from the fall and all that good stuff, and use that energy to project itself back up onto the table.
So it can't use any other energy in any other rational way, because that energy is going in the wrong direction also, going into the ground in all kinds of different directions. There's no way to create a reflector that would reflect just those little discrete pieces of motion.
That doesn't violate the first law of thermodynamics, but we never see that happen. In fact, we're so cocky that if we saw a video of that, we'd say, oh, they ran the video backwards. Okay? So
in running videos backwards really doesn't work explicitly, because friction you can't make go backwards. So the fact that if it's rolling stuff, then it's going to slow down, and air resistance, you can't undo the fact that something will end up speeding up. If you reverse the video, something slowing down will look like it's speeding up, and you'd say, well, why would something speed up? I already launched it, it already hit and had contact. It can't go faster. Friction can't make it go faster, and it would appear as though the friction was making it go faster. So reversing doesn't really work in almost any condition, because there's no way to get completely out of gravity. So theoretically, there's no place where we could even experience that idealization where there wouldn't be a force that wouldn't be reversible. There wouldn't be an influence that you can't reverse without a preposterous conflict where you're creating a paradox, where something moves without energy being applied.
Turns out to be the essence of the second law of thermodynamics. Is it tells us what things are probable and what things can happen, and also, of course, what things can't happen.
So we know the second law of thermodynamics is just mush, that there's any way that energy just goes in one direction, because it clearly doesn't. It goes in both directions, and we're collecting it in both directions all the time. Gravity is a energy building force, and we're capitalizing on it. We're stealing, through hydroelectric, we're stealing the energy of gravity. All right. And then you have other forces where the sunlight is an energy deprecating force. Okay, the sun is giving away energy, and we're collecting the dispersal of the energy from a higher level of radiation to a lower level of radiation. It's It's not, again, we can't steal it. We can only use it for a period of time. So that's the other part, I guess, that has to be emphasized. There should be some law that basically states you only use energy for a period of time. You occupy it. You take advantage of its possession, and then it continues on its course. You never use energy. Okay, you you rent it. You don't use it up. You don't consume it. You can't consume energy. After you use it, it has to be dissipated as some other kind of motion, heat, sound, something. It has to go somewhere. It can never just be used up. And it's really important. And no physicists just don't say it that way.
Okay. So that's what we need. Now, it turns out we first started studying this uh, when we were making heat engines. Like I told you, for instance, we use the weird sine problem with the first law of thermodynamics.
So I don't know why this idea of a heat engine and calling the steam engine a heat engine really isn't accurate. I mean, it's like any other engine. Basically, it's going to create pressure. It's going to create expansions. And we're going to take advantage of taking something that's small, heating it up, making it very big. Steam is an incredible, water has an incredible expansion rate. So you're talking about 1,000 times more space it takes up when you got it hot enough. There's huge advantage to taking advantage of that pressure, the expansion. And that's what they're pressure engines. I mean, it's kind of, I just don't think it's fair to the argument to call them heat engines. But of course, heat is integral to this expansion process. So you could say that a rocket is a heat engine. But, come on. Is it really about the heat, or is it just about the fact that you're going to expand a huge number of atomic bits of atomic structure? You're going to, it's taking up a tiny amount of space, and you're going to make it take up a huge amount of space. And just take advantage of the fact that that's going to create a lot of pressure.
So it's very different from chemistry. Specifically, we say the change in internal energy is equal to the heat added minus the work done by the system.
So the work done is also a lie, because work is kind of just describing one part of any heat equation or any energy equation, and we just consider somehow the stuff we like or we want we'll call work, and then the rest we'll call something else heat or waste, and it's all the same stuff. You can't deny its existence. So if you're doing work, that is, you're creating some kind of productive work, and you're creating heat also, well, yeah, the heat is the waste. It's a waste of your energy because you don't want the heat, but it's the same thing. It's momentum lost. You're using momentum in both sides of that equation. It's just that you're saying one of the momentums we don't want and one of them we really do want.
That's because we were developing these thermodynamic principles thinking about the system being some kind of heat engine, and we really were curious how much work the heat engine was putting out. So that was the thing we focused on, as opposed to the energy coming in and energizing the system, which is what the chemists were thinking about, which is why they said Q plus W and we said Q minus W. Okay. So
that's kind of convoluted in terms of adding the work as being something that is a part of I don't know how it could ever be considered a waste, but they're not separate things. You're going to create work and you're going to create some inefficiency. You're going to vibrate the air, you're going to make noises, you're going to do other things that aren't going to be considered what you're gaining out of the process. But there really shouldn't be a word called work. All of it is the function. The function is you put energy in, you get energy out. It's always that equation. The same amount of stuff moving in the universe is always the same.
all that came to be. And of course, what we're going to get is the very first statement that your book gives on the first law of thermodynamics, or excuse me, the second law of thermodynamics. I don't know how many times I'm going to say first law when I mean second law, but anyways, your book opens up in the very beginning chapter, or the very beginning of chapter 20. I think this is, I can't even remember.
So let's just make my argument, just in case you're still listening. That that obviously gravity breaks all of this nonsense about energy having to die as free energy, that is, as photons or something, some kind of discrete radiation. It doesn't die. The radiation is always hitting another object. So the sun radiates heat. It can reflect off the earth. It can hit another planet somewhere. It can hit something. It's always going to be somewhere. It never is dead. I mean, obviously, if you're going to have energy conservation, you have to have some way to take the discrete energy produced and put it back in the system. So we know that gravity gives things momentum. I mean, the obvious one would be this. Okay, that's momentum. It was given to the object from no other function than gravity. Gravity gave it to it. It obviously now will create heat when it hits the surface of the Earth. And I would argue that the deeper point is why it's sitting on the surface of the Earth. It's melting the center of the Earth because it's just another piece of pressure that will continually push on the center of the Earth, creating a bunch of conflicting pushes, which are going to be a bunch of jiggles. Okay, you can't cancel the energy. It can only push that way, and then you can turn left. The steering wheel has to go left. It has to go right. It has to go left. It has to go right. It never just sits here. So anytime there's the appearance of cancellation, there really isn't any cancellation. There has to be heat. And so the force that isn't a force, gravity, this bent geodesic nonsense, is creating energy in the system. So the second law wouldn't mean anything in the context of you have a constant source of new energy. And so the simple solution is, well, it's not new energy. That all of that cosmic background stuff and the stuff that we can't detect, I mean, we can assume there's photons we can't see, broken pieces. We could break a photon with a polarizing film or some other thing. We take it out of phase. We can't see it anymore. The energy's still there because it didn't melt the polarizing film. So we know the energy's still there. But we can't detect it. We don't have an instrument to detect the broken photon. So I'm just saying all of this energy's out there. We know about the cell phones and we know about the microwaves and all the other stuff hitting us all the time. All we have to do is say, well, there's some other stuff that we can't detect because it doesn't have frequency. And that's actually the energy going back into the system. That's what's pushing us into the Earth. So the second law is really bad science because there is no tendency to go one way. There's just as much of a tendency in the universe to build suns as there is to explode suns. It's thermodynamically at equilibrium. There's as much photons and radiation being expelled by objects as there is radiation pushing them into round balls and making them hot. The matter is consuming the energy and then radiating it. That's not complicated. The Earth is molten because of the gravity. There's no other reason that the Earth is hot. And I guess per foot or per meter of Earth, you could say that it's 200 degrees Kelvin as some sort of average. But all of that heat of that gigantic mass has all been created by gravity, by the absorption of force trying to get from one side of the Earth to the other side, and it has to jiggle a bunch of stuff to do it. It spends a lot of time jiggling atoms inside the Earth before it gets out the other side as a piece of radiation.
Remember the page number, but it doesn't matter too much. This is an ebook. The second law of thermodynamics, and this version is called the Clausius statement, due to R.J.E. Clausius, who lived from 1822 to 1888.
So this is the important part, is there's two definitions of the second law. One definition is the old heat argument, that somehow, that Clausius kind of perceived everything is declining as the energy getting tinier and tinier until it's not useful anymore and it's not even heat anymore. So, but that's just because he didn't really have a better view of the universe and atoms and electrons and protons and all of that crap. So it's because of the knowledge he didn't have that he had some perception that you couldn't recover that heat and turn it back into a burning sun, when of course you can. All right. And then the second definition is the one just about the probability arguments of scatter. So you're just basically saying is if you convert energy that's going in one direction, like the electrons moving in a wire are forced to travel one direction. So it's very useful energy. And if you scatter it as a bunch of photons going all over the place, well, yeah, you can only catch, some tiny percentage. You can only use some small percentage that's containable, that's catchable. Something like that. Alright, I guess I should point out I haven't seen this part, but I'm assuming he's just going to defend the notion that somehow heat drifts into uselessness when energy drifts into uselessness, when I obviously am arguing it can't do that and be conserved. How do you turn heat into bent space is the real point. Bent space obviously creates heat. So how do you turn the heat into bent space? Seems I hit the wrong button somewhere. Anyway, okay, back. So I haven't watched this video this far, and so I'm assuming he's going to say the heat drifts into non-utility, into a form that can't be recycled back into the system. And obviously I would argue that bent space is a bad idea right on its surface because it obviously creates heat. It generates the motion that creates heat. And therefore, how do you turn the heat into bent space? There's no logic to it.
Time frame is about the same as when people were developing Maxwell's equations and that sort of stuff. But his name was RJE. In other words, his initials were RJE Clausius. And the second law of thermodynamics, according to Clausius' statement, is heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. So what I'm expecting you to do in this chapter is every time they mention a version of the second law of thermodynamics, I want you to write that down verbatim along with its name. And I don't need you necessarily to memorize it so that you could recite it. That's asking a little more than is really necessary.
Yeah. So I suppose it's a good idea to have all these different definitions for the same law, right? So that's the problem. You have a law, you call it the second law of thermodynamics, and there's probably 5 or 6 statements by different physicists reinterpreting the statement into completely different statements, frankly.
What I'm asking you to do with that is be familiar with it enough that you can identify it out of a list, as I explained to you earlier. So that was the first statement. And I tried to go through the book and I actually highlighted like that, for instance, and all the other versions so that one, I highlighted it and then I told it to share. And that's supposed to make all the highlights that I put available for you, my students, to see it. But what I've noticed is it's not necessarily showing up. So if you look in your book, you might not find the Clausius statement to be highlighted. In my book, it looks like it missed the second law of thermodynamics title and didn't start highlighting in the.
Yeah, that's unfortunate. Yes, okay, this is a bunch of insider stuff. But anyway, jump a little bit ahead, see if we're back on the subject.
So we're finished with section 21. Section 20-2 talks about heat engines. And let me give you that diagram that I promised you regarding a heat engine. So now that I've discussed that a little bit, what I'm going to tell you is a heat engine is something where we have what we consider a heat reservoir. So heat reservoirs, if you remember what we talked about in chapter 18, I think it was, or 19, a heat reservoir could be pictured as like a lake. Okay, so you could do experiments on the lake, like literally sit up, a little floating table and do your experiments on the lake. And if you had experiments that were thermodynamics related, you could say, okay, well, I'm going to use this lake to cool off my utensils when I'm doing these reactions and stuff like that. And what's going to happen is,
Yeah, so that's, we're back to Joule, which is sort of interesting in terms of how physics didn't do anything to build on what Joule created, was the idea of inventing a machine, a device that would actually collect energy. I mean, that was what Joule wanted to do. He wanted to compare steam engines to electric motors, and he needed a way to know real information. He didn't want to hear about horses lifting water, and he didn't want to hear about all kinds of bullshit. He wanted to know exactly how you took this much fuel and you put it in, what did you get out in terms of how much productive work could they create, how much total was available, let's put it that way. And and so you need a way to quantify the energy you're putting in and what total energy you're getting out. And so that was the whole idea of heating water, because it heated in a consistent rate, took a certain amount of, it has a certain density, it's consistent, and it's rather containable in terms of you can, insulate it and measure how much work you did by how much you raised the temperature of the water. And just the fact that physics did nothing, so since whatever 1870 or whenever it was, they did nothing to utilize that procedure as a way of measuring. So we could have really precise data about how much energy the bullet has versus the recoiling gun, because they could just shoot them into a Joule tank and measure how much they raise the temperature of the water. And we could find out if the bullet has 2,000 joules and the recoiling gun only has 2. Okay? So, and I'm clearly going to state that no, they have the same quantity of motion. 1,000 atoms moving 1 mile an hour is the same as 1 atom moving 1,000 miles an hour. It's the same units, quanta of energy. And the fact that physics has left all of that ambiguous and underdone. They could drop 4 pounds 1 foot into the water, and then they could drop 1 pound 4 feet into the water and demonstrate that those are the same amounts of heat. They're the same amount of energy, when clearly they're not. And we'd find out that, yes, 350 years ago, Leibniz was what he appeared to be, a junk talker. Okay, he just talked crap. He didn't show anything. He didn't prove anything. He just stated it as an axiom. And that's it. And the whole kinetic energy theorem is built out of garbage as evidence. And it's disproven by levers. It's disproven by spaceships. It's disproven by the fact that we landed on the moon using momentum. It's disproven by all of it. And yet physics clings to it and has used it to invent a whole idiotic standard model that wouldn't exist if mv squared didn't exist.
At any time, you can dump any amount of heat you want to directly into the lake, and the lake's temperature is not going to change because the lake is so ginormous. That's what a heat reservoir is. It's something you imagine it's immune from changing temperature no matter how much heat you take from it or how much.
Well, see, that's just cheating then, right? So even Carnot knew that you can't cheat. So that's the inefficiency that's built in, is that you will take energy out of your heat source. You can't do motion for free. It's always going to cost some energy. So something, the cold thing has to get hot, or the hot thing has to get cold. There's just no other way around it.
Heat you put into it. So that's what a reservoir is. With a heat engine, we're imagining a high temperature reservoir from which heat can be extracted. So this high temperature reservoir is going to cause a difference in temperature because it's a high temperature, and it's going to cause that heat from that high temperature reservoir to enter into the heat engine, whatever the heck that turns out to be. That heat engine is going to take as much of that as it can and convert it to work. And that work could be stuff that does like kinetic energy or makes potential energy. We remember it as work equals the integral.
So I just pick on the potential energy point because it's just such a misused word. Because the thing that has the energy is not being properly identified. So the boat sitting on the side of the Mississippi River, it would be stupid to say it has potential energy because I can stick it in the river and let it sail, or be drifted or pushed by the river for 500 miles. and then to say it has the amount of potential energy that has to do with how long the river is. If the river's only got 20 more feet, and then there's a waterfall, well, and I can only move the boat that 20 feet, it doesn't mean that the boat has 20 feet of potential energy. So the whole idea of calculating gravity based on how far something can fall was just nonsense. It's about how long it's going to be in the river, and it's about how long you're in the gravity that's going to decide how much force you collect, how much momentum you can extract from the river. The river goes slower because you take energy from it by your boat. Your boat adds mass. That mass dilutes what the river has as energy, and it's all conserved. You take it from the stream. So something held up in gravity, it's just wrong to say this has potential. It doesn't have anything. Doesn't have any energy. It doesn't have any storage. The storage is in letting it flow in the river. So if I tie a rope to a boat and it's can't go where the river's pushing it, obviously I'm going to have to apply a force. I'm going to have to compensate for the energy to make it not move, and that's just a fact. And the energy is in the river, and it's just, again, I'm just saying, it's, I think, making a logical error not to understand gravity is doing exactly that. It is perfectly analogical to a force of raindrops. It's paint. We're getting sprayed with it, and we're getting sprayed with more from the open universe than we're getting sprayed by the shielded Earth. The Earth is stopping the stuff from getting to us, slowing it down by pushing a bunch of matter, so it doesn't get to us, and the stuff from the universe is free to hit us, and so we get hit by more per unit of time coming down than coming up. Kind of obvious, frankly. I mean, it's so obvious that to defeat it and believe in some wooey bent thing, nonsense, space-time, you should have really good evidence. And they don't have really good evidence.
Of F dot DL. Now, one of the versions of the second law of thermodynamics says that you can't take all of that. Okay, if QH comes in, you're not going to get QH turned into W. You're going to get something smaller than QH turned into W, and whatever's left is going to be called Q sub L, and that's going to be the heat that's released into another reservoir. In this case, it's a low temperature reservoir, and you're going to dump that exhaust heat into that low temperature reservoir, and because it's a reservoir, it's not going to change as a result of that low heat. So in
theory, right, you're taking a medium temperature, you're taking a hot thing going into the medium temperature, and then you want to get rid of the heat after it does its work, after you use its directionality. And then you want to take the heat it recreates. The motion's going to recreate heat. And you want to drain that heat so you can restore the condition back to a medium temperature so you can pull the hot in again. And so that's why Carnot had this perception of a one-way cycle. But it doesn't apply to the rest of the universe, because the rest of the universe is a closed system, and all of this heat from every single place, we're all in it. We're all getting bombarded with it constantly. And the heat is really just momentum. So we're constantly in a momentum engine. And you can't escape the momentum. It compresses things. The compression creates radiation. The radiation creates compression. The heat, the motion compresses us. We have to radiate it. We radiate it, and that ends up compressing something else. So everything's radiating an energy that compresses everything else and causes it to radiate the energy that compressed it. So it's a closed cycle, and it's therefore conservative. As Descartes pointed out. I mean, Descartes described in a simple way, whatever God is, it doesn't matter, because what God did was start the universe rolling, you know, threw the energy in, and the energy stuck inside of it. Okay, and so the God doesn't have to poke with it because it's all being just transferred energy.
Car, you can imagine the high temperature reservoir, say, as the exploding gas that you pour into the piston or that you put into the piston from your fuel pump, and
So again, it's just another example where you're just taking molecules that are very small and making molecules that are very big. And that's, you know, the fuel has a huge expansion rate, you know, 10,000 or something, 10,000 times bigger. And so that's why gasoline is so useful as a fuel, is because of that huge expansion rate.
uh, electronic emission, or excuse me, uh, your carburetor would be the easiest thing. But there's also, of course, things that we use instead of carburetors now, and I've just lost the name of that.
Fuel injection, but it's okay.
But electronic fuel injector, that's what it's going for. So that fuel injector or carburetor sort of sneezes that mixture of oxygen and gasoline into the piston, and then the piston closes on it, attempts to crush it or to condense it, or basically contract it quite a bit. And at the instant that that piston gets to the peak of its motion, where the volume inside the cylinder is the smallest, there's supposed to be an explosion caused by a spark running across the spark plug. If it's a diesel engine, you won't have the spark plug, but the same thing happens. It's just with a diesel engine. The compression is such a large ratio that it explodes on its own.
Well, that's not really true. There's just hot plugs. So you just heat the hot plugs. But anyway, same thing. They don't need an actual spark to ignite it. All they need is a hot plug.
But that hot temperature reservoir is sort of what you're thinking of, because guess what? Once you've ran the engine for a good minute or so, the engine block is going to be a very high temperature, and it's going to stay that temperature, and it's not going to appreciably get hotter or colder, more or less, no matter how long you run it. So that is a high temperature reservoir. And then the gas, after it's been exploded and caused that force stroke, which is actually pushing, meaning giving the force that can turn the shaft, and that shaft is going to cause rotation that goes into your transmission, and then the transmission can re-gear that and send that out through your drive shaft or into your axle directly, for instance, if it's a front wheel drive. But either way, when it hits that, it's got to go through the differential, where it can actually encounter more gears to change ratios.
Yeah, so there's all kinds of inefficiencies, and all of that creates more radiant heat. So it's more loss of the stuff going in one direction. So that's all you're really just saying, that the only way energy is really useful is like a laser beam. It's all going in the same direction. And anything that starts to scatter it, okay, means that you just can't use it. Your water wheel needs the energy to be in the stream, you know, that kind of thing. You need it to all be going the same way to really use it, to capitalize on it. Because if it's spreading, then you have to make a gigantic collector to collect it all, right? So it's too difficult to collect energy that's spreading in this part of the universe, big places. If it's spreading in a tiny little atom inside of a cylinder, well, then it's all contained, and so then the explosion can all be captured. And it doesn't matter that the energy is going in all directions, because you're closed the system, and you want the pressure to push it apart. I suppose there's always that negative side where the explosion takes place and you really want it all just to push on the piston, and a lot of it is wasted pushing on the cylinder and making the cylinder hot.
Especially in the rear end of a vehicle and so on and so forth.
So I guess ideally you want the walls of the cylinder to stay hot, because then they can't absorb more energy. They're more likely to reflect it. So the hotter the walls of the cylinder are, the more efficient the engine becomes, because it's going to lose less energy to heating a surface that's already hot.
After that force stroke is there, then another stroke will come by and compress the gas again, only this time when it's compressing the gas, it's spitting out the burnt gas out of the output. and that goes out the tailpipe into the atmosphere, and our atmosphere doesn't change appreciably because your tailpipe's putting out hot air. Okay.
Well, obviously, one individual car doesn't heat it appreciably, but there's clear evidence that a whole bunch of cars are heating it appreciably.
So that's sort of the picture of what an internal or of what a heat engine is. So now I'm going to give you an actual drawing for it that we'll reuse repeatedly, and it's super helpful in trying to make sense of a heat engine. So let me go ahead and show that to you.
So some of this, I think, we've already been over some
It
of
should
this in
pop up
previous
any minute now.
videos. So,
Okay. So here's what we're going to imagine.
all right. So yeah, we probably won't do this part. Let's see what it comes down to. Let's see how the drawing. The drawing's not evolving much, is it? Oh, there it is. All right. So he's got a cold and a hot, and he's just using one simple. Obviously, the heat engines are invented to be kind of sophisticated in terms of how they move objects, and so but like I said, I've been through some of that with a previous video. So lots of different ways of doing it to increase the efficiency with which you transfer the heat, move it. But the more important part of this video was just to get to the second law, and he's sort of done with that, and he's just going to do heat engine analysis, so we won't bother with the rest of that. So anyway, we'll see if we get anything as a reply, and call it a video and such. Yeah, I think so. So till the next time, and such, and so forth, and whatnot. Yeah. So I can't, I just comment on his video with a link, but it doesn't work. It's unfortunate. I can't use my Draft Physics channel. I can't use my DraftScience YouTube channel to comment on the internet. Okay, YouTube's preventing that. And it seems that it blocks most of the comments from my Inmendum channel, so I can't even use that channel to make comments on videos without them disappearing. So it really does suck, that I really, I mean, YouTube should be caught playing all these damn games, with this disappearing, just pretending it's some sort of malfunction that these comments are all disappearing all over the place, because they can just use it as an excuse to discriminatorily mistreat people, and it seems obvious that's what they're doing. It doesn't seem like a coincidence that both my channels would be broken in this particular way, in different to different degrees. It's just bullshit. But anyway, till the next time, and such and so forth and whatnot. Thanks, Bill. And I really am looking forward to a response. I know I have no right to think that a physicist would feel at all obligated to defend their physics, but you're teaching it, so you should be willing to defend it.